Welcome back to the next session of operating systems. In the last class, we have seen process synchronization introduction. So let's just go through what is process synchronization. So in process synchronization, we will be looking at the background. We have seen the background, the critical section problem, the Peterson solution, and we also had started with synchronization hardware. So next we have to see Mutex Locks, Semaphores, classical problems of synchronization, and monitors. So let's go through the background and till the hardware, synchronization hardware. Okay. So processes can execute concurrently. I have already told you that one or more processes are executing simultaneously in the system, either through a multi-processor system or a single processor system. But there are multiple systems who are working, or multiple processes that are executing simultaneously, and during this process there can be some shared data or files which are used by two processes simultaneously, two or more processes simultaneously. So in this case, there should not be a case where the two processes manipulate that shared data simultaneously. The code in which such a manipulation happens is called a critical section problem, and we have to take care that there is consistency maintained in manipulation of such shared data. Example is the producer-consumer problem, wherein the producer is producing products and adding to the stock of the market, whereas the consumer is consuming the products and decreasing the cost in the market. So in this way, the addition of products and the deletion of products from the stock, or the number of products that are there in the market, should be consistent. It should not happen that the number of products that are presently available in the market are 5 and producer produces 5 more products, so it should be 5 plus 5, 10, and consumer has consumed 3 products out of those 5 products. So total number of products should be there in the market is 7. But what happens if both producer and consumer take the value 5 at the same time and manipulate the value at the same time? So in that case, the producer will say 5 plus 5 is 10, and the consumer says 5 minus 3 is equals to 2. So I said producer is producing 5 new products and adding to the stock, and consumer is consuming 3 products and decreasing the cost. So in this case, both have used the value 5, which is the current stock in the market, and one of them has increased the value by 5 and another has decreased the value by 3. So in this case, producer says that in the market the stock is 10 products, whereas the consumer says that the products that are there in the market, the stock that is there in the market, is only 2 products. So who is correct in this? Both are wrong. So we have to take care of such a situation. That is what is process synchronization. So let's quickly go through this. So we saw that how this manipulation happens. Whatever I have explained just now in words, the same thing is in algorithm. You can just go and see the previous video to understand this algorithm execution. I also told you in the last class about race condition. So what is this race condition? When two of them are simultaneously taking, the producer and the consumer is taking the stock market value as 5 products that are there in the stock, and they are manipulating it. Because they both are manipulating at the same time and are getting the different values, so we call that as the race condition. Here we are explaining the race condition. So here, producer executes in register 1 load count. What is the value of counter? Counter right now is 5. Then he says increment it by 1. So register is having the value 6. Next, register 2, the consumer is loading into register 2 the counter value, which is again he has taken 5 values. So both producer and consumer have taken 5 value simultaneously. So these instructions are executed simultaneously by the two processes. So now counter is 5, so counter is stored at register 2, and then it is getting decremented. One consumer is consuming 1 item. So in that case, the counter value is register 2's value is decremented by 1, so it will become 4. Now, counter is updated by both register 1 and register 2. So, producer is also manipulating counter, consumer is also manipulating counter. So, in this way, they will both manipulate the counter value to 6 and 4, which is wrong. Why? Because the counter value should have been 5, because one is being produced and simultaneously one is being consumed. So the counter, the stock in the market remains the same. So this kind of situation is called as a race condition. When two processes are racing to change the data simultaneously, we call that as a race condition. Next one is critical section problem. So I told you the code in which such a shared data is manipulated is called as a critical section problem. So if there are in a system n processes and each process has a critical section segment, then they all can manipulate common variables, updating tables, writing to files. All these are the scenarios wherein there can be a critical section problem. So critical section is designed to solve such a problem. So each process must ask permission to enter into the critical section, and in this entry section it should take the permission and may follow in the critical section, and then it can have an exit section and then the remainder section. So this is a basic structure of your critical section problem. So this is the structure. If you will see that in words, you can put that into a general structure. So we have a do while loop, which is an infinite loop, and in that we have an entry section, critical section, exit section and remainder section. So in the entry section, they should take a permission, the processes should take a permission to enter into the critical section. So any process that wants to enter into the critical section, it takes permission, executes critical section, then exits the critical section and then goes into remainder section. In the exit section also it has some tasks to do. So here is a general algorithm for two processes, you can say, or n processes. But if you take two processes I and j, this will work like this. So here while turn is equal to j, if turn is jth process turn, then here there is a semicolon. Can you see this semicolon? This semicolon indicates that you do nothing but you repeat this while loop. So while turn is equals to j, when it is somebody else's turn, I am going to wait. I am going to wait for that other person to finish. When the other person finishes his turn, then only I can go and execute my critical section. After I execute my critical section, I will have to tell that other person, yes, I have finished, you go ahead. So we are here in the exit section, we are saying turn is equals to j, and then the process enters into its remainder section. So there are three requirements that any critical section problem should solve. One is mutual exclusion, second one is progress, third one is bonded waiting. What is mutual exclusion? Mutual exclusion means only one process should enter into the critical section. At any given in any process, there will be only one process who is executing the critical section. Other processes who want to enter and execute their critical section, they cannot do that until unless this running process does not out of the critical section. So that is mutual exclusion. Second one is progress. Progress indicates if there is n processes that are waiting to enter into the critical section, who will enter next? If there is postponed indefinitely, has to be done in a specific amount of time. The decision of who is going to enter the next has to be decided. So if among your 10 friends, if there is one person who wants to, there are 4 persons who want to enter into the critical section, then only one can enter, and who that one has to be decided in a given amount of time. Cannot be infinitely postponed. Next one is bonded waiting. All the processes that are waiting to enter into the critical section, then in those who enter the critical, only those processes who have already entered into the critical section cannot again enter into the critical section. So once a process makes a request to enter the section, the other processes who have entered the section cannot enter the section until unless this process does not enter. What does this mean? Supposing there are 5 and one person has got an opportunity to use. If you have and there are 5 people in the, there is only one. That car can be used by the 5 people, but if anybody makes a request that he wants to use the car, then the person who who has already used the car or who is running the car, who is using the car right now, cannot use the car until unless this person's request is not, the first person's request is not satisfied. So that is what is bounded waiting. So any process must wait for a finite amount of time. It cannot be made to wait and others cannot be utilizing it continuously. So that is what is about, in this we have made an assumption that all processes are of zero speed, non-zero speed. Every process is having some amount of speed. It is not necessary that they have a relative speed. One is executing faster and another one is working slower. It's not having any relation, but they are having a non-zero speed. We also saw that operating system also implements critical section problem, that this solution can be different in a primitive and a non-primitive scenario. If it is a primitive scenario, then a running process can be preempted and hence the operating system has to take care of it by providing some locks. But if it is a non-primitive software operating environment, then the process will never be printed and hence the critical section problem will not arise in such a situation. So I have discussed this in detail in my last video. You can just go and see there. We also discussed the Peterson solution. This is a very old solution. Nowadays, newer architectures, this solution may not work because of two reasons. Because first one, it's old, and second one is that it works only with two processes. But here in now modern days, there are more than two processes that will be working on a critical section. So we have this algorithm just as a sample, because it's a very simple and basic algorithm to understand how the critical section problem works. So in this case, we have two variables like you see here, turn and flag of 2. So flag is an array of 2. Turn indicates which process has to go next into execution, ith process or the jth process. And flag indicates that if the flag is set to true, it means that that process is ready to enter into its critical section and it is seeking permission to enter the critical section. So this algorithm assumes that it uses the load and store machine level language instructions, and these are atomic instructions. Atomic means that these instructions cannot be preempted. When it's executing, this is load and store instruction is getting executed, no other process can preempt the CPU. So it cannot overload, so it cannot override. One process cannot override the other process. It cannot remove that running process and it cannot execute itself. So that is what is the meaning of this. So let's understand this algorithm. This is the algorithm. I have already explained this algorithm in the last class. So we here I and J are two processes. So in this is the ith processes algorithm. Similarly, you can write the jth process algorithm. Wherever there is I, you write J, and wherever there is J, you write I. So that is the jth process algorithm. So in this case, flag of I is equal to true means PI process is ready to enter into its critical section, and before it can enter into its critical section, it is saying turn is equal to J. The turn is equal to J indicates that it is saying that I am ready to go into the critical section, but let the other process, if it is ready, let it go and execute its critical section. After it finishes, then I will execute the critical section. So there are two processes only. So it says that I am ready to execute the critical section, but I will wait for the other person to finish the execution of the critical section. So that is what is the meaning of this. Turn is equal to J. So in this case, if flag is equal to J and turn is equal to J means the other process is ready to enter. If its flag is true, it means J's process is ready to enter into its critical section. So if flag of J is true and turn is also J, we have only said that turn is equal to J in the previous instruction. So we need to see whether flag is true or false. The Jth process flag is true or false. If it is true, that means that process is wanting to enter into critical section. So we will say let it finish the execution. Till then, we are going to make a wait here. So the while loop here with a semicolon indicates that it is looping and doing nothing. It is just waiting till the other process finish the critical section execution. So when the other process finishes its critical section execution, then only the flag of that process will be made to false. When that flag becomes false, this condition becomes false. Flag of J false and true. Turn is equal to J. So this condition becomes false. When this condition becomes false, the process PI enters into the critical section. When it enters into the critical section and executes this critical section, before it exits, it makes its flag false so that if process Pj is waiting to enter its critical section, then it can enter the critical section. So we make the flag as false. Even this is in the process Pj also. Pj also, when it is exiting from the critical section, it makes its flag false to indicate that I am not interested in entering the critical section right now. I have just finished my critical section. So that is an indicator to the other person that you can enter the critical section and execute the critical section. So that is Peterson solution. Now does Peterson solution achieve all three requirements of a critical section problem? Yes, we have seen that in the last class, right? So we know that mutual exclusion is achieved with that flag J and turn is equals to I. So that while loop at the beginning, there we are achieving mutual exclusion. So if the other process wants to enter the critical section, then we will allow them to enter, and when it finishes, then only this process executes its critical section. X progress also is achieved. We are setting the flag at the exit time, we are setting the flag to false. That process which has just finished the critical section executes, flag is equals to flag of itself is equal to false. So that indicates that it is taking care that the other process who are waiting can enter the critical section. So there is progress. Then there is bonded waiting. Bonded waiting, because we are making exit at the exit time, we are setting false. If there is anybody who has made its flag true, then it will, and as soon as it has made true, and this process makes its flag false, the other process can enter into its critical section. So that is how it is achieving the mutual exclusion, progress and bonded waiting. Then we saw the synchronization hardware. So what is synchronization hardware? I have already told you in the last class that hardware provides one synchronization technique is that it provides a lock. So any process who wants to enter the section has to achieve that hardware lock is set. That is, the CPU is locked. The CPU is locked, and hence no other process can achieve. So that is one way. Second way is in a uniprocessor system you can disable interrupts. Disable interrupts. Then once the allocated it will execute the and then only way we are mutual exclusion process. And then we have, but this is not the case in multi. You are getting the advantage of having a multiprocessor. The thing will be reduced. The efficiency of the multiprocessor is reduced because you cannot scale it as you can with interrupts enabled. Because if there is interrupts, one processor is busy, another processor is free, then that another process can take up the new process that has requested for CPU and it can start execution. Now two processors are busy, third processor and fourth processor. You have a quad-core processors. So four processors are there. So that way it will go on giving the execution task to other CPUs. So we cannot disable interrupts on a multiprocessor system. So we can have modern machine also provides special atomic instructions, like atomic means non-interruptible instruction. So once that instruction starts execution, then CPU cannot be taken from such a process. So we can have two such non-interruptive methods. One is test memory word and set value, and second one is swap contents of two memory words. So first let's see the lock, how lock works. We have finished this also in the last lecture. So first you need to acquire a lock. After you acquire a lock, you enter into the critical section. Then you release the lock and then go into the remainder section. So when you are going into the remainder section, you are making the lock free for any other process who wishes to take this lock and enter its critical section. So in that way we are achieving this. So this is test and set. This is the method wherein we are saying, taking a value, target value, we are saying assign that target value to a Boolean variable RV, then set the target is equal to true, and then return RV. So this is executed atomically. This method is executed without any interrupt, and it returns always the original value passed to the parameter and sets the value of the parameter to true in this method. So how this is used? So here we have a shared Boolean variable lock initialized to false. So this is a do while. I have written this algorithm here. Just let's see. Now we are here in any process. So this is a process's code. In this process, this is a critical section, and in this, to execute this critical section, it has to make this condition false. When this condition is false, then only it will execute this critical section. You can see here, there is a semicolon. This semicolon indicates that if this condition is true, do nothing. Are you understanding? There is no instruction in this while loop. There is a semicolon. This semicolon indicates that do nothing if the condition is true. If the condition is false, exit the while loop. So this semicolon itself is a while loop. This while loop, this much block, in the while block, there is only a semicolon and it says do nothing. A loop with a semicolon and no statement indicates do nothing. It's just a loop which is simply checking the condition, and it waits till the condition becomes false. So that is what is happening here. So while test and set ampersand lock. What is the value of lock assigned? Initially it is false. So lock is false. So here target is false because test and set is this method. So to that method the parameter passed is false. So target is false. So we assign false to RV, and then we make target as true. Right? We are changing the value of target to true, and then we are saying return RV. What is happening here? RV is having the value false. So false is returned here. False is returned, and after false is returned, what is the value of target now? In this target, we are passing it as the pointer. We are using a pointer. So pointer is nothing but, target is nothing but, for lock, target is another name. So target initially is false, and in this method the target is making this to true. Target is changing the value of lock to true because target is another name for lock. Okay, so lock is set to true. What does it mean? That if the lock is false, then only you can enter the critical section. Once the lock is made true, then any other process who has come to this instruction will see that it is having the value false. What is the lock value now? It is true. So it is true. So here, when we come here, what will happen? This is not false now. It is true. Then this is also true. RV is assigned true, and target is again true. So target lock is true, and we are again setting it to true, and we are returning true. So other process who is trying to enter its critical section, it will get the value of set and lock as true. So it will keep on waiting till that becomes false. When will that become false? When the process who first set the lock to true will not make it false. When the first process, the process who is executing the critical section, has to set the lock value to false. When the lock value becomes false, other process, so if P1 has done lock as true, then P1 sets the lock to false. So any PI other than P1 can make the lock again true, execute this, and come to critical section. Did you all get it? So I hope you all have got it. So this is how your set and lock, test and set works. Next one is on the similar line, we have the compare and swap instruction. So just note down this compare and swap instruction. In this, there are three parameters that it takes. One is value, next is expected, and next is new value. So in this case, these are integer values. If you see that, there are integer values. Again, value is a pointer variable here because that is a one which is being used by everybody to check whether the critical section, anybody is executing in the critical section. If nobody is executing in the critical section, then any process who wish to execute the critical section can enter the critical section by compare and swap. So this is again it is executed atomically. It means that the instruction, this entire method, when it is getting executed, no other process can execute this instructions. No other method or no process can preempt this process. So next, returns the original value passed by parameter value, and the set variable value, the value of the passed parameter, new value. But if value is equal to expected, that is swap takes place only under this condition. So what is happening here is this expected value and value initially is 0. It indicates 0 indicates false and 1 indicates true. It means that if the value is 0, it means that no process is executing in the critical section. If the is 1, it means there is some process who is executing in the critical section. Other processes who want to execute the section will have to wait till the value becomes 0. So similar to this, here we were having true or false, and there was lock and target. Here we have value, and expected is that the expect value is always 0 because we want that the process, the critical section is not having any process executing in the critical section, and we want to enter the critical section and execute the critical section. So expected value is 0. Okay, and new value indicates that the lock is not available. So false, the true condition. So it should be, it is 1. The new value is 1. So let's see how this is used. So here we say that shared integer lock initialized to 0. Here also the shared integer lock is initialized to 0. Do while compare and swap ampersand lock 0, 1 not equal to 0. So when the while condition should not return 0, it should return 1. If it returns 1, then 1 not equal to 0, it will enter the critical section and execute. So here this method compare and swap ampersand lock 0 and 1. So initially lock is 0, right? And expected value also is 0. So if you see here, the value here is 0, the expected value is also 0, and new value is 1 according to what is being passed. So 0, 0 and 1 because lock is 0, no? So 0, 0, 1. 0, 0, 1 is passed to this method. 0, 0, 1 is passed. Okay. So int temp is equals to ampersand value. So assign value to that. So what is the value of value? Value is having the value 0. So it is the values are 0, 0 and 1. That is been passed, right? So we are saying now temp is equal to 0, which is the value. Okay. Next we have if star value if the value is equal to expected. Value is 0, expected is 0, both are 0. If both are 0, then we say star value is equals to new value. What is new value? New value is 1. Right? So what we are doing, if both are 0, that means what is lock value and expected value. We want that we are expecting that the lock should be 0. If the value is actually 0, then both are same. So we are setting the value to 1, and then we return target temp. Sorry, we return temp. We return 0. So when we return 0, what happens to this method? So here, compare and swap. What is returning? It is returning 0. 0 not equal to 0, condition is false. So in this case, it will wait. It will wait for the process who is there in the critical section to finish its execution. When it finishes its execution, then it will make the lock 0. Just a minute. This is actually return there is a mistake here. Actually, it should return value. Actually, it should return value. So when it returns value, okay. So if the value is 0, now the new value that is assigned to value is 1. So 1 is returned here. So in that case, what will happen? Then 1 not equal to 1, then it becomes true. So when 0 is equals to 0, sorry, it should be temp only. That's correct. Only when it returns 0, 0 equals to 0 will become false. So here in this case, the value that is returned from compare and swap is 0 and not equals to 0. 0 is not equal to 0 will become false. That time it will enter the critical section. So if any other process who wants to enter into its critical section now, what is the value? The lock right now is 1. Lock value is 1. So in that case, here there will be a 1. For any other process, the value will be 1 here. So temp will be assigned 1. Then what is this? This is 1 and this is 0. The value is 1. Expected value is 0. So new value that will be assigned is also 1. Here that is this condition is only false. So it will directly return temp. This will not happen only. So because star value and expected value are not equal, it is not equals to, the condition becomes false and we return temp. So other process who is trying to acquire this lock, because the lock value is 1, so it means that when lock value is 1, it simply says that, indicates that some process is executing in the critical section. So other process who wants to enter the critical section will have to wait till this lock becomes 0. So when this lock becomes 0, when this process who is executing it in its critical section assigns the lock value as 0. So when lock is assigned 0, then only this process goes into remainder section, and other processes who are waiting to enter the critical section, they will get the lock value as 0. So as soon as this lock value becomes 0, this becomes 0, this is 0, and 0 equals to 0 is true. So value will be assigned 1 and 0 will be returned for that process, and that process will enter into its critical section. So that is how your compare and swap works. So in this compare and swap and test and set both methods, there is a problem. The problem is that it has no bounded waiting. Why it is not bounded waiting? Bounded waiting means what? That means if one process PI wants to show an interest to enter into its critical section, then the other process who are and there are other process also who are waiting into the critical to enter the critical. If I say that there are n processes P1, P2, P3 like this. Supposing I have P1, P2, P3, P4. four processes that are there in the system, and all these are concurrent processes. Then P1 shows an interest to enter into its critical section. Nobody is in the critical section, so it enters into its critical section. Meanwhile, P2 also shows its interest to enter the critical section. P3 also shows its interest to enter its critical section. P1 finishes. As soon as P1 finishes, P2 enters its critical section. Now P3 has showed its interest to enter the critical section, but before P3 enters, P1 enters into its critical section after P2 finishes. So what has happened? P3 has made a request, but who has entered now next? P1, who has already finished execution of the critical section, and P3 is waiting. Now P1 finishes, but P3 doesn't enter, P2 enters. P2 enters its critical section. So what happens? P3 is still waiting. So if this way, then next if P4 also comes into the picture, it also says it wants to enter. After P2 finishes, P4 enters critical section. P1 enters critical section. P4 enters critical section. What is happening to P3? P3 is continuously waiting because all others who have already finished execution also are again repeating the execution. But P3 is not getting a chance to execute its critical section because it has registered its interest long back, but it is not able to execute the critical section. That is what is bonded wait. There is no bonded wait in this system. So we are not taking care of these two algorithms are not taking care of bonded wait. Any process who has just finished the critical section also can come back and execute the critical section. We are not telling that if I have finished, let the turn be the other person. So in the previous examples of Peterson solution and all, we are saying that turn is equals to J. In PI process, at the exit section, we said turn is equal to J. So I finish, you enter. We were allowing the other process to enter the critical section. So here, in the previous two examples, we didn't have the test and set and swap, compare and swap two methods. Those two methods didn't have this bonded waiting criteria satisfied. So how can we do that? To do that, we put one more level of condition, so that way we can achieve this critical section bonded waiting. So what we do is, we say waiting of I is equal to true. So any process who is waiting will make its process, will set a flag for every process that its waiting is equal to true. So let's take these four processes and try out this solution. Now, supposing P2, waiting of 2 is set to true. That means it is ready to enter its critical section. Next condition is, next we are saying key is equal to true. We assign key is equal to true. Next what we say? While waiting of I and K. While waiting of 2 and key. If this condition is there, so waiting of 2 is true and key also is true. Both conditions are true. Since both conditions are true, we are saying key is equals to test and set ampersand key, right? Set ampersand lock. So let's go to test and set. What was test and set? Test and set was Boolean. Then what we had? Boolean RV is equals to, sorry, this was target. We say star target. Star target is equals to true, and then return RV. So this was our second test. So what is the value of lock? Initially lock is false, right? So here false is sent. So we get target is equals to false. So RV is equals to false. Target is equal to true. So lock becomes true now. So we are accessing lock indirectly through target because it's a pointer variable. So we are setting lock is equals to true. Then return RV. What is returned? RV means false. So here he is returned, gets the value false. When he becomes false, so here this is false. So this condition becomes false. When this condition becomes false, we will come to the next statement. What is the next statement? Weighting of I is equal to false. So weighting of 2 was true. A weighting of 2 will become false. Why? Because it is going to enter the critical section. So it enters the critical section, and while it is executing the critical section, supposing P3 also makes its weighting as true. Weighting of 3 is equals to true. Now this is not weighting. Supposing again weighting of 1 is equal to 2. So P3 is waiting, P4 is not waiting, P3 is waiting, and P1 is waiting. In this time, meanwhile, when this P2 is executing its critical section, P3 has shown interest to enter its critical section, and P1 has shown interest in entering its critical section. So in that case, when it finishes critical section execution, it calculates the value of J. What is the value of J? J is equals to I plus 1, right? I plus 1 mod n is what is the value of J. What will be J now? What is the value of I? I is 2. So let's calculate. 2 plus 1 mod, what is the value of n? N is 4. So what you all will get? 2 plus 1, 3. 3 mod 4, remainder will be 3. So it will wait. It will calculate the value of J as 3. And then while J not equals to I, what is the value of J? J is 3. What is the value of I? I is 2. So this condition, I not equals to J. I not equals to J. While J not equals to I, and weighting of J. Is Jth process waiting? Is the Jth process waiting? What is J? J value is 3. What is weighting of 3? Weighting of 3 is true. So it means that to call the method called as acquire lock, and when it finishes its critical section execution, it should call the release lock method. So the calls to acquire lock and release locks must be atomic. Obviously, they should be atomic because they should not be interrupted when it is executing. So Boolean variables indicate that if lock is available or not. So if acquire returns true, it means that yes, you can start execution with the critical section. Acquire, release will make the flip-flop between the Boolean values, true to false and false to true. So usually implemented via hardware atomic instructions, but this solution requires busy waiting. So this is also called, that's why it is called as a spin lock also. So let's see how this works. So this is the method for your acquire and release method, and the method and the process which uses this critical section, which is having a critical section and uses this acquire lock and release lock method. So you see here acquire lock. So how does this acquire lock work? We have acquire lock while not available, go into busy wait. That means repeat this while loop, go on executing this while loop until unless the available becomes true. When the available becomes true, then you will get an opportunity, this process will get an opportunity to enter its critical section. And releasing at release time, available will be made true. That means any process who wants to execute its critical section, we will say that the critical section is available for execution. So available is equal to false means what? Which means that the critical section is being executed by somebody, hence other process who want to enter their critical sections, they cannot enter the critical section. So here you see a process. So before it executes the critical section, the process should acquire the lock and it should release the lock before it goes into the remainder section. Next is semaphores. Semaphore is another simplest way of executing process synchronization or having critical section problem. So this is a sophisticated way of Mutex Locks to execute Mutex Locks. It is a process of synchronization and it is actually executed as an integer variable, and s is the integer variable that we use, and can only be accessed via two individual atomic operations, wait and signal. These are the two operations that you all can perform, that is wait operation and signal operations. These wait and signal operations were previously called P method and V method. P indicates probe and V indicates this thing. So it's a Dutch method name for wait and signal. So definition of wait operation, here it is, wait for S while S less than or equal to 0, busy wait, you go on keep executing the while loop, otherwise decrement the S. So what does this mean? So in this case, it is not one instruction, it is more than one instruction, more than one semaphore can be for more than n processes. For you can use it as a counting semaphore. Semaphores can be binary semaphore as well as counting semaphore. A binary semaphore means it has 0 or 1, as we have seen in the previous example. So a counting semaphore is the one wherein we will have incrementing and decrementing this thing. So if there is a resource R, and if R is having n instances, then S is the semaphore that will take the value up to n. So every time a process who wants to take this resource, instance of a resource, it will check their semaphore's value, S value. So it will decrement S by 1. So if there are n instances, n minus 1. First process who takes the resource instance, it will make it n minus 1. Means how many instances of that resource are available? Supposing if this has 5 instances, first process requests for that instance, one of the instance. What is the resource and instance? Resource is nothing but the hard components that are available on your system. Take for example the number of USB ports on your system. There are 3 or 4 USB ports on your system. So what is the number of instances of the USB ports on your system? 3. Are you understanding? So there are 3 instances of one resource, USB port. So here like that any resource can have, supposing there are 5 instances of that resource. So first process P1 comes and requests for the resource. Then how many instances will remain? P1 is granted. So only 4 remain. Next, P2 comes and requests for a resource. P2 is granted, so number of resources left are 3. So every time a resource is taken, so initially S is 5. First process takes, S becomes 4. Second process takes, S becomes 3. So like that, if 5 processes take, S becomes 0. That means number of processes P1, P2, P3, P4, P5. All 5 processes have taken an instance. Sixth process comes in P6 and requests for that resource. Then S becomes negative. S becomes -1. What does it indicate? First of all, for all 5 processes, we have given the instances. Whatever 5 instances we had, we have given all the 5 instances to first 5 processes that requested it. Now, sixth process has come and requested for the same resources instance, and there is no instances available for allocation for P6. So, it means that how many processes are waiting? One process is waiting. Supposing P7 comes and makes a request, S becomes -2. So just take this numerical value. What is this? This indicates how many processes are waiting to acquire a resource instance. So that is why we have here --. So whenever a process wants to request for execution of the critical section, it decrements, and whenever it finishes, the signal always increments. So here, supposing now P1 finishes its execution, if P1 finishes its execution and releases the resource, so X will be incremented, so it will become -1. So it means that P6 will be allocated the new instance that was just released by P1. P2 releases the instance, then S becomes 0. That means P7 gets the instance that was released by P2. So that way it goes on incrementing. So if P3 also releases the instance, then S becomes 1. That means one instance of that resource is available. So that is what is the simple technique of semaphore. So how does semaphore usage? I already told you that there is counting semaphore and there is binary semaphore. So counting semaphore, integer value can range over an unrestricted domain, and binary semaphore, integer value can range only between 0 and 1, same as Mutex Locks, and can solve various synchronization problems. Consider P1, P2 and requires S1 to happen before S2. Supposing there are 2 processes. There is P1 process and P2 process. Then there is statement 1 and statement 2. The condition is that statement 1 should execute before statement 2. So whenever process P2 wants to execute statement 2, it has to wait for the synchronization. So when is this synchronization takes place? When S1 finishes execution and makes a signal. So when the signal is made, then only this wait will end and the process P2 can execute the statement S2. So this is a simple. So it's not necessary that it is a critical section problem. It can be conditional execution also. So here in this case, it's a conditional execution. It means that the statement S2 cannot be executed by another process until unless one process does not execute statement 1. So statement 2 execution depends on statement 1. So it has to always wait for this process to finish execution of statement 1. So Semaphore implementation, it must guarantee that no 2 processes can execute wait and signal simultaneously. That is the important thing. So this itself is a critical section now. Okay. So thus the implementation becomes critical section problem where wait and signal code is placed in critical section. So we say that the wait and signal itself are going into the critical section. So what we could we could have a busy waiting in the critical section implementation. So but implementation code is short. Little busy waiting in critical section rarely occupied. So if there is less of the critical section code, then there will be very less time for busy waiting. So you manage that. But if the critical section is very large and takes hours together to execute, having a while loop executing or a busy wait is a waste of the CPU because the CPU is even executing that while loop without any statement. You have seen in the previous example, so many examples, we have while and semicolon, right? So that while statement, it is just repeating the while loop and checking the condition every time just to see whether the condition has changed, right? So that statement execution of just checking the while loop to see the condition is changed is using the CPU, which is the waste of the CPU energy, which could be used by some other process. So this process could be put into a waiting list and we could execute the another process. So this needs that there should be semaphore waiting queues. So note that application may spend lots of time in critical sections. How the solution is that with each semaphore there is an associated waiting queue. So we'll have a waiting queue. So if semaphore, there is S1 semaphore, we'll have one waiting queue for S1. If there is semaphore S2, we'll have another waiting queue for S2. Any process who wants to execute, who is waiting for semaphore S1 and semaphore S1 is busy, then we'll put that process into the queue. And when any process who is executing in the critical section for semaphore S1, it finishes its critical section, we will allow this process to execute. So we will see how this works in the next class. Thank you. We'll continue in the next class.